Hello, this is going to be a code walkthrough for the final project that I did for this class. I'm just going to do a quick walkthrough of all the stuff that I did to get the system up and running the way it is. So here goes. So I'll start off with my main file. At the top, I have all of the pound includes for the stuff I need. I needed the UART, the ADC for the joystick, clock configuration, LCD driver, PWM for the output SPI for controlling the LCD, and then the LCD driver that we were provided by the instructor. I have values for keeping this value is used for debalancing the circuit for the switch. This is to keep track of which menu option we're at, and this is to keep track of which mode we're currently operating in. I have the UART handler for the menu, the ADC handler for the joystick, handlers for the SPI device and the LCD, and then PWM handlers. I also have lookup tables for the sine wave and the triangle wave. These were generated at the websites that I've linked in the code. And then I've just plopped them in here. They're used as lookup tables for the PWM to be used. Uh, so, and then finally I have a global variable to keep track of which lookup value to use in the actual PWMing process. I start main by initting how, sysclock init, UART init, and then ADC init. I initialize the SPI and the LCD screen. And then what I do first things first is establish a idle value for the y-axis on the joystick. I take an average of 16 samples, and then I treat that as my idle value. And then I have the current value for the ADC. And then I print the menu out to the screen and then fill the screen with color and then draw a sine wave on it because that's the default function that we initialized to. And then I start up the PWM with sine wave output. And then for the rest of the code, basically all I'm doing is sitting inside of this loop and monitoring the ADC value. I keep getting average values from the ADC. And then if the joystick is being tilted up, then I move the current option up. And how this is printed out on the menu it will be in the UART file. And then I do the same thing for moving it down. Then obviously I have bounds for if we're on the first or the last value in the menu. And that's all that main is. Main's pretty simple. Most of everything else is done via interrupts and stuff like that. So moving on, I'll start with the clock configuration because there's a few changes from what we had before. This needs to say 64. So basically what I have is the clock initialization that we had from the very beginning of the class. Everything, however, is changed to 64 megahertz. Previously, we were using APV1 set to 32 megahertz. I have it set to 64 to give me greater frequency output on the PWM since the timer 3 is hooked up to APV1 and the clock tree for the STM32. That's the only change here. Next up, I have the ADC initialization. I changed some of the I/O. I'm using GPIO A pin 0 and 1 for the ADC channels, and then I have pin 4 on GPIO A configured to the switch button on the joystick. And then these are all functions that I wrote in the past for the ADC lab. The only change here is that I have the GPIO callback in the ADC function. The reason I put this here was because it was this is kind of like the joystick driver of the code. So I wanted to just go ahead and put this in here for the for pin 4, which is configured as an input interrupt. So basically what this does is this callback, what it does is we first debounce. So there's a 200 millisecond debounce on the circuit. And then the first thing I do is I stop the timer, stop the PWM timer, and then obviously that's done because any option that we have in our menu actually changes parameters for the the timer. So I wanted to stop it and then start it after I'm done all the processing. Um, the first thing that happens is we check if it's pin 4, if it's pin 4. So um, I look to see if it's current menu option 1. If it's current menu option 1, that is increasing the frequency. So to increase the frequency, we subtract the prescaler, but we only want to increase the frequency if the prescaler is not already set to 0. So that's just a check in place. Next up, to decrease the frequency, we have to increase the prescaler. And then I increase the prescaler and do a PWM init to pass in the parameters. For operating in a sine wave, operating with a sine wave, I pass sine mode to the current mode variable, which if you recall was defined in main up here to keep track of which mode we're operating in. And then I draw a sine wave onto the LCD. And then similarly, I do the same thing for the triangle and square wave. And then finally, once all of that's done, I restart the PWM, and then I set the interrupt to make it so next time we debounce, we know what timestamp we debounce the circuit at. This is called in the XTI4IRQ handler. So I just have the callback with the pin 4 as the input, and then I clear the interrupt for GPIO pin 4. That's all for the ADC. Next up, we have, I'll talk about the UART. For the UART, this is configured the same way that we had the UART configured all the way back in like lab 4 or whichever one we were using the debug UART in. I have all of that code in here. One new function that I added in was this print menu function. I have the menu here, which is 0 through 4, increase frequency, decrease frequency, sine wave, triangle wave, square wave. I start off by clearing the screen. This is the menu. This is the command to clear the screen that I found online. This was linked on Stack Overflow. I print like a little border to show that a new menu is being printed, and then I sit in a for loop that prints out the whole menu. And then if the current menu option is equal to I, then I print out the cursor, which is these 3 greater than symbols. And then otherwise I just print out 3 spaces. That makes it look nice and clean. Let me open up TerraTerm, and I can show you how that looks. Oh, I need to change the baud rate to 115200. So yeah, as for some reason, clearing the screen causes the menu to move down like that, but I haven't figured out what how to fix that. And so as you can see, moving the cursor up and down, this is all happening because of this, because of over here, we're incrementing this current menu option, and then we print out the menu every time. So that's all being done. Every time we trigger a joystick event, then we do this routine or this routine, and that's what's causing us to scroll up and down on this menu like that. From here, what we have is the SPI interface, which is all frankly the same as what we had before. I haven't changed anything here. For the PWM output, I have I'm using channel 1 of timer 3 now, as opposed to the previous one that we were using. I think that was channel 1 on timer 1, I want to say. I think that was on GPIO port A, which if you recall, I'm using as the switch input for the joystick. So I have that configured here. Now the only change is as far as the PMW IRQ handler, which is called whenever the PWM triggers an interrupt on the timer 3. Um, I have the different modes now. So the sine mode, and the triangle mode, we have lookup tables for these. And then for the square wave, if the lookup table is less than half, if the lookup index is less than half of what it needs to cycle through, I just set the pulse to be period, and that allows the PWM to be on for the whole period of the clock, for 128 out of 100 out of 256 of the samples required to generate that square wave. And increment the lookup table index at the end every single time. Um, so from here, I just integrated everything together. I don't think I forgot anything. We talked about the LC. Oh, sorry, the LCD driver. I did write some new code for this one. Um, so I added 3 new routines for this guy. So the first thing, the things I wanted to add were the routines for drawing the different waves onto the LCD screen. First of which is the square wave. For these, I use lookup tables again. I'm becoming quite fond of using lookup tables to do all this stuff. So basically, I wrote some lookup tables by hand from scratch, and I basically sit in a loop and use the lookup table values with some coordinates on the XY to position the square wave onto the LCD screen in a way that it looks appealing, and then I draw some vertical lines for the transitions and the falling and rising edges of the square wave. And I kind of follow a similar approach for the triangle and sine wave, where I have lookup tables for them, and then I just sit inside of 2 loops, inside of this loop, and then another loop to print it again, to create a nice looking pattern. And the sine wave's the same way. And if you recall, these were called in the IRQ handler for the, I think it was this file, for the pin, so for the switch input. So every time the current menu option is 2 and we click the button, we change the current mode to sine wave, and then we draw a sine wave, and then do the same thing for triangle mode and square mode, and then start the PWM again. So the reason I was running into problems with drawing these waves on the LCD with the PWM still going, I think that's because if the system's in the middle of drawing uh, an LCD, drawing something to the LCD via the SPI, and it experiences an interrupt, it enters the LCD enters a bad state, and you have to reboot it. So to mitigate that, I just stopped the PWM and started again. That just ended up being the best answer for also updating the LCD screen. I suspect if you I don't think there's actually a real good way of updating the LCD screen with the PWM still enabled, because it'll, like, I think like a million times out of 1,000,001, it'll go ahead and cause the LCD to enter a bad state. Um, but yeah, that's about the gist of it. I I ran into a few problems with the lab, particularly the problem where the frequency output of the PWM was not as high as I wanted it to be. I wanted to give the user better fine-tuning resolution for the frequency, but it turns out with the prescaler the way it is and the clocks on this board, that resolution's not quite possible. I suspect if we had a better timer clock, a faster clock for the timer, we could probably achieve some better rates, and then make it so that actually tuning the frequency was possible. But it doesn't really make sense to have that type of resolution when changing the prescaler by even a value of 1 causes such a drastic change. So to demonstrate that, if I have, I'll go as fast as I can. So this is as fast as I can go. Um, and I'll put some cursors on. And I'm just gonna put this here. I think this gives me a nominal operating frequency of like 250. or so. Okay, so 240 hertz, right? This is with a prescaler of 0. Um, and then if I go ahead and decrease the frequency, so the prescaler is now set to 1, I'll hit single, and you can see what a drastic change that is. So like here, the frequency went down by like 80 hertz just by changing the prescaler by 1. And I wanted to initially have tuning that was like increased by 5 hertz, or increase by 5 hertz and decrease by 5 hertz and increase by 10 and decrease by 10. But that's not really possible with the prescaler, because the clock's too low for that prescaler to the clock's too slow for that prescaler to give us the resolution that we want. Um, Nominally, I recommend running this. I recommend running this system and adjust the system to boot at a prescaler of 3, because that's what causes the output to look the best. But as we can see, that basically cuts down the frequency down to like 97 hertz. That's not ideal. So um, in the future, if I were to do a project like this again, I would probably spec out the frequency of the clock onto the PWM, and also do some math to calculate how fast the PWM can go before I get started. Um, I integrated the PWM into my system last when I was doing this, so I encountered this problem very, very late into the project, and um, 2 days before the due date, it didn't make sense to start on a new project. So I just went ahead with it and uh, kind of improvised by just decreasing the resolution that the user is given and going with this type of setup. But yeah, I think that about wraps up everything I had for this project. I wanted to say thank you because I had a good time with the class overall. I learned a lot. I think I'm ready to tackle some embedded systems problems. Um, so, yeah, thanks again.